Hello, thanks for tuning in. Sorry we weren't able to finish these notes for everybody, but I want to make sure that we're all on the same page. Alright, when we're dealing with our circuit models, what I like to use is a gravitational model. The component over here, which in the animation, remember, is moving in this direction, that's what the arrows are for, is basically an escalator. And so the escalator is raising something from an area of low gravitational potential to an area of high gravitational potential. Basically like going from the first floor up to the second floor. Now notice, all of this up here is on the second floor. That means it all has the same potential as the top of our escalator. Down here, this is all on the ground floor. This is all at the base of the escalator. Now, our escalator represents a battery. A battery has a symbol like that, either 2 sets or 3 sets of long lines and short lines. The long line is the top of a stairwell or escalator. It's basically the high voltage part or the positive side of a battery. The small side is the negative side of a battery. And across this thing we have a voltage difference. And it's rather accurate to put a delta V on it, although usually we just say V. And so let's say here we have a potential difference of, I was going to go with like a small battery, but let's use a bigger battery because we have larger fields down there. So let's say it's 12 volts. All right, so we got a car battery. Right? Car batteries are 12 volts. Or for that matter, we have 8 1.5 volt AA batteries linked in series with each other, so they add up to be 12 volts. Okay, that is the potential difference between this part and this part. Now, this wire which is connected to it, which then goes to a resistor and then back. Okay, our resistor is the pinwheel. Now, notice there's only one path for the current. So this here is our simplest. We refer to all of these as simple circuits. This I like to think of as the simplest circuit. It has one circuit element, one resistor, R. It has one battery of voltage V or delta V if you want to get technical about it. And it has a current that flows around the whole thing of value I. All right? It has only one current because it only has one pathway. These positive charge carriers have no place to go other than along in the path. And so they keep going uphill, they keep sliding down the slide and turning the pinwheel, and all they're getting done is they're turning this pinwheel, which is the equivalent of like having a light bulb. Now, if we have 12 volts here, and just because that one kind of looks like the resistor that we have here, let's say that that's our 30 ohm resistor. 30 ohm resistor, then the current from Ohm's law. Now we only have a couple of laws here. One of them is Ohm's law, V equals IR, and a second one which is a statement for power, how much energy is used up. Power is current times voltage. If we combine these two, we can get the other versions of power, such as substituting this in here, we could get current squared times resistance, or we could also get substituting in current here. I'm sorry, substituting in, current, that's voltage divided by resistance, so that would be times voltage again. So we would have voltage squared divided by resistance. Our current, which is the most basic thing to answer, is going to be equal to our voltage divided by our resistance. We've only got one voltage, one resistance here, and so that is 12 volts divided by 30 ohms. 12 divided by 3 would be 4, so this is divided by another 10, so that's 0.4. So 0.4 amps is our current for this one if we were interested in figuring out how much energy is dissipated by this bulb per second. Okay, basically how many watts this resistor is pulling. Then our power in that case would be that singular value of current times the times the voltage, not times the resistance. which would be 0.4 amps times our voltage. Now hold on a second. We never figured out what the voltage is across the resistor. If it's going up by 12 and it goes through one resistor, this wire is all at positive 12, this wire is all at 0, so it's dropping through 12 volts. So we also have a 12 volt drop across the resistor. The 12 times 0.4, let's see, 48 plus another decimal, so 4.8 watts is what is being used up by that one if we were asked about power. They do have power on the formula sheet. They could ask about it. Now, if we have resistors in series, our resistors in series, I'm going to call this one here R1. I'm going to call that one R2. I'm going to say that my voltage here is still 12 volts. First thing you usually want to figure out is what is the current. We are going to only have one value of current because we only have one pathway. To figure out the current, we need the equivalent resistance. The sum of resistors in series is equal to the summation of the resistors R1 plus R2. So that is 30 ohms plus 10 ohms, so that's 40 ohms, nice and easy. If I wanted to know what is the voltage drop across this resistor, and what is the voltage being used up by this resistor, now we are talking about Kerkoff's loop rule, which says when you go around a full loop, the change in voltage is 0. Here it's gaining voltage, here it's losing voltage. Okay? So the voltage gain is equal to the voltage loss. And so that means that V is equal to V1 plus V2. That is Kerkoff's loop rule. Now, defined V1 and V2. Well, first I'm going to need that current. So the current coming out of the battery is equal to the voltage across the battery divided by the total resistance of the whole circuit. And so this is our 12 volts divided by our 40 ohms. And so 12 divided by 40, it would be 3, so 0.3 amps. Okay, so voltage across resistor 1. How much of the voltage is used in this first one? How much is used in the second one? For the first one, it's going to be the current that's going through resistor 1, which is just the one value of current, so it's just I, times the resistance of resistor 1. So that means 0.3 amps multiplied by our resistor 1, which is 30 ohms. And so it's going to be 9 volts. So V1 is equal to 9 volts. Now I could do the exact same thing for the second one, and that would be simple. Or I could go back to this and figure out that voltage 2 is equal to the overall voltage out of the battery minus voltage 1. So in other words, it's 12 minus 9, so it's equal to 3 volts that is used through that one. If I wanted to answer any questions like how much power is being consumed by this one, how much power is being consumed by that one, that would be really easy. Now something we should notice about power is that the total power for a circuit is equal to, just like in series, just like the resistors in series, power from the first one plus the power from the second one plus however many you have. Okay? Because of conservation of energy, if it's being used here and here, or here and here, it's got to add up because that energy came from someplace. And power is the rate at which you are using energy. Let's just get our sketch for our circuit in here. We've got our battery at 12 volts. We've got 2 resistors. Now, they don't have to be one here and then another one going vertical. I could put another one here. This is also in series. So this is R1 being equal to 30 ohms, and this is R2 equaling 10 ohms. And this was my 12 volt battery over there. And of course, my current is coming out of the positive towards the negative for one value of current around the whole thing, which was 0.3 amps. Now, parallel circuits are a little bit harder. This was a series circuit. This is a parallel circuit. Parallel circuits, the reason they're harder is we have branches for our current. Now remember, Kerkoff's, now the overall current coming out of the battery, we usually call I, right? Because it's going through the battery of voltage V. This being R1 is experiencing V1. This is R2, that's V2 that it has flowing through here. Current I1, this has current I2. I2 is going this way at this junction. I1 is going that way, although you can't really see it in there so much. I1 goes this way, I2 goes that way. That is Kerkoff's junction rule. And so quite obviously, I is equal to I1 plus I2. That's conservation of charge. It's not allowed to just disappear anyplace. In order to find I, or to answer questions like how much current's going through resistor 1, we first have to find the total resistance. This is a parallel circuit. That means this offers some resistance, this offers some resistance. The total resistance will be less than the resistance of this alone, because this is given an alternate pathway out, and it will be less than the resistance of this alone. So it will be less than our smallest resistance. So it should be less than 10. Up here, it was bigger than our greatest resistance. Down here, that's what happens in series. In parallel, it is smaller than your smallest resistance. All right. 12 minutes. I better start moving along here. Okay. Now, my equivalent resistance, 1 over the sum of my resistances, is equal to 1 over R1 plus 1 over R2. Luckily, there are not more of them. And so that means it's 1 over 30 ohms plus 1 over 10 ohms. All right. Need a common denominator, so that's 1 over 30 ohms, 1 over 30 ohms plus 3 over 30 ohms. So 1 over the sum of my resistances is equal to 4 over 30 ohms. Now once you get it to this state, flip the whole stupid thing over, unless you get something that's really easy. So that means that the sum of my resistances is equal to 30 ohms divided by 4. All right, let's see, 1/2 would be 15, so 1/2 of that is 7.5. 7.5 ohms is the equivalent resistance of the whole circuit. It is less than our smallest one, it is less than 10, so we did it right. Once we have that, we can find the total current. The total current is equal to our voltage divided by our total resistance, and our voltage again is our 12 volts here. And so that's 12 volts divided by 7.5 ohms. Now I want to grab a calculator because that one doesn't want to behave. 12 divided by 7.5. How about if I turn it on first? 12 divided by 7.5. We get 1.6. Not too ugly of a number. 1.6 amps. All right. So if I have my overall current, I can figure out how much current goes through this one. Now, here's a important thing. Here's the top floor, here's the bottom floor. Notice the tops of each of these slides hits the top floor, they all end up on the bottom floor. That means they've all got the same voltage as they all have the same voltage as the battery. In a series circuit, everybody has the same current. In a parallel circuit, everybody gets the same voltage, because this has a straight line back to the positive terminal, so does this. This has a straight line to the negative terminal, so does that one. So if I want to know how much is current 1 and how much is current 2, current 1 is going to be equal to voltage 1 divided by resistance 1. Voltage 1 is the same thing as the battery's voltage, so that's 12 volts, divided by 30 ohms, which means it is 0.4. Right? So 0.4 amps. Now, if I did the same thing, I could subtract it because Kerkoff's junction rule says that this one plus that one adds up to that one, but let's just double check. And so current 2 is voltage 2 divided by resistance 2, and so that is voltage 2 is the same as the voltage of the battery, so 12 volts, divided by R2, which is 10 ohms, and so that's 1.2 amps, and look, this one and this one adds up to be that one. We've verified Kerkoff's junction rule. Also notice this one has 1/3 the resistance of that one, and so it gets 3 times the current of the other one. If we were asked any additional questions, such as what is the power consumption of the second resistor, we could then go back to our power formula to find that, now that we know all the values about this resistor here. Okay, thanks for watching. Sorry we couldn't quite wrap that all up in class.